Hello everybody, welcome back to my YouTube channel. In this video, we will cover what LSTMs are, and believe me, this is the most detailed and most simplified video on LSTMs. If you are someone who feels that LSTM is scary, believe me, by the end of this video, you will say that LSTM is super easy. So stick with me, subscribe to my channel because that gives me motivation, and give this video a thumbs up. Let's start. So this is the architecture of RNN, and this is the architecture of LSTM. And by looking at these two architectures, definitely this one is the scarier one, right? But believe me, this is way more simpler than it looks. So let's just first understand that what is the problem with RNN? Why do we feel the need of having something like LSTMs, and why RNN didn't work? The reason was very simple. RNN is like a guy who forgets older stuff and remembers only what has happened with him recently. So if RNN is given a short sentence, then it will predict the next word with a very high accuracy. But if it is given a long paragraph, and if we ask it to predict what will come at the place of dash, there is a high probability that it will forget the context and give the answer purely on the basis of what it has seen recently. So there are high chances that if it sees the sentence I drink hot, then it will perfectly predict that either coffee will come here or tea will come here. But if it is given a long sentence like this one, like I grew up speaking Spanish, I moved to the US 20 years ago, and now I work there as a software engineer. At home, I still speak. Then it will only remember this information, right? And on the basis of that, there are high chances that RNN will say English, right? It will forget what was being told to it previously, right? So technically and by logic, Spanish should come here. So RNN fails when there are long sentences because it is not able to retain memory. It tries to remember everything but forgets older stuff. And that is where LSTM shines. LSTM chooses what to remember and what to forget. So instead of having a single hidden state like RNN, it maintains two states, one to capture the short term memory and one to capture the long term memory. So it has hidden state just like RNN, but now it has an additional cell state which is called the memory cell state, or simply the cell state that captures the long term context. And well, this is how human brain works, right? You how do you whenever you read a story, how do you maintain the context? You carry two types of memory, long term memory and short term memory. What is currently happening in the story, that is being stored in the short term memory part, and what happened previously, that is being stored in long term memory part. Now, the moment you read something recently, then on the basis of that you update the information in the long term memory. Let's say you were reading a story where there was a king who was very famous, and then entire description about that king has been done, and now his son has come into the picture. So now, based on the recent information that you have read, and you can basically update whatever you have in the long term memory. Maybe you can completely remove the king's information if that is not relevant, as you read the entire story. It was just for the introduction, and the whole story is around that king's boy, right? So it it can selectively delete, it can selectively forget, it can selectively add information. And it's not like it will completely forget the king, but it will retain it until the time it's 100% confident that now it can remove the information about king, because it is no longer discussed, or the king, or the story is no longer discussing anything about the king. Or maybe it might retain a very little information about a king. For example, he is that boy's father. So that is how these two memories coordinate between each other. And RNN is very simple, because you have an input, you get an output, and that output is then again being sent as input in the next state. Right? Now in LSTM, you not only have one memory, but you have another memory here, which is called the long-term memory, that goes as input. Right? So here this and this, they both are going as input along with xt, then processing is happening, and then you're getting, actually it should be ct minus 1 and ht minus 1, because this is coming from the previous LSTM, and then you get the latest ct and latest ht as outputs. So I think you now know that why RNN failed and why LSTM shines. There are mathematical reasons behind RNN failing, like the vanishing gradient problem and exploding gradient problem, which we will discuss in detail while we will make a video for RNN. But since this video is dedicated to LSTM, so I've just given you a brief overview that why LSTM shines and RNN fails. Now, LSTM works just like human brain, where we maintain two contexts. First one is to just understand that what's happening currently, and the other one is to maintain the long term context. And instead of having a single hidden state just like you have in RNN, here you have an additional cell state in order to capture the long term context. So this was a brief introduction about RNN, why RNN fails, and how LSTM shines. Now we will see a detailed overview of its architecture. Now we will dive deep into this part. So let's go. So to understand the architecture of LSTM, this is our LSTM architecture. And in order to understand this, we must first be familiar with all the notations that are being used within this particular architecture. And we will use these notations throughout this video. So I just want to make everything clear that these notations, they are very simple, and currently they might be looking very complex, but the moment I will explain all of them, this architecture itself will become much more simple. So let's start with the inputs. So in our architecture there are three inputs. First one is xt. This is our xt. Next is ct minus 1. This is our ct minus 1. And the third one is ht minus 1. ht minus 1. Now this t here is the current timestamp. Okay, the current time step that we are considering. And t minus 1 is the previous time step. So if xt is the input at the current time step, then ht minus 1 and ct minus 1 are the memory inputs that are coming from the previous LSTM or the previous time step. Okay, and this ct minus 1 is actually cell state, that is the long term memory that is maintained by LSTM, and this ht minus 1 is hidden state, this is short term memory that is maintained by LSTM. Okay, and this xt is actually a vector like this. Okay, it's generally 1 cross n, where n can vary depending on what is the dimension that you have chosen. Now this xt, let's say you have a very long sentence, right? You have a very long sentence. For example, I love apples. Then this xt, let's say I am at time step t equals to 3. That means my third word will go into the architecture, right? This will go as input. So this word, we can't directly put words inside the model, right? Because model understands only numbers. So this word is converted into vector embedding or simply a vector. And this vector is then sent inside the architecture as input. So xt is nothing. It's the vector of the word that is going as input at the current time step. Okay, and this ht minus 1 and ct minus 1, these are coming from as they are coming from the previous LSTM. Now you might wonder that what if we have this as our first LSTM, then this and this will be nothing but a vector of zeros. Okay, and here since the length of this vector can be any, it could be 1 cross 3 or 1 cross 4, but LSTM has a rule that the length of this vector and the length of this vector, they has to be they have to be the same. Okay, so if length of this vector is 3, for example, if we have 1 cross 3 vector here, then our ht minus 1 will be exactly of that same dimension. Okay, it will be 1 cross 3. So this is rule of the LSTM. This you have to keep in mind. Now let's consider output. So once all the processing will be done inside, once all the processing will be done, you will get two outputs. The first one is CT, that is the cell state at current time step. Okay, and second one is HT. This is the hidden state at current time step, and this same output is going out from here. Okay, so that is why you see three arrows. One is for the long term memory, that is LSTM is maintaining. This is our cell state at current time step, and these two arrows are for hidden state or the short term memory that the LSTM is maintaining. Okay, so I hope these input output notations are clear. Now let's move to in between processing that is happening and what are the different notations that are being used. The first one is FT. Now what this FT is, this FT is the output that is coming from here. It's a vector. Now it's okay if you don't understand what kind of vector it is, what kind of processing is happening inside it. We will cover everything in detail. I'm just clearing the notations here that what is FT, from where it is coming. Only that I'm clearing. The entire processing we will cover later. So this FT is the output that is coming from here. You can think that there is certain processing that is happening, and this processing takes ht minus 1 and xt as input, then certain processing happens here, and then we get ft as output. Okay, similarly we take ht minus 1 and xt as input, then again certain processing happens here, and the output that we get here is called it. Similarly we have xt minus 1, I mean ht minus 1 and xt, that they go as input, some processing happens here, and what we get as output from here is called C dash T. And this OT is the processing output of the processing that's happening here. What exactly the processing is, what exactly is happening inside these boxes, we will cover that when we will discuss the fifth point. Okay, so these are nothing but the outputs. And what kind of outputs these are? These all are vectors. These all are vectors. And what is their dimension? Their dimension is equal to the dimension of these vectors. Okay, so this vector, this vector, this vector, this vector, each of these vectors shape will be equal to the shape of these vectors. So if there are three elements in CT minus 1, then FT, IT, C dash T, OT, all of them will have three elements. Okay, and all of them will be vectors. Now let's move to the fourth one. What are these circles that we see here, we see here, here, and here also? What are these circles? So these are nothing but pointwise operators. Pointwise operators. So what kind of pointwise operators they are? These operators are applicable on these vectors. Okay. So first one is multiplication. We take two vectors here. Let's say 1, 2 and 3, 4. I have taken two vectors here. Then this is pointwise multiplication. We take every element and multiply the corresponding element of another vector. So 1 cross 3, 3. 2 cross 4, 8. So this is what the output of this pointwise multiplication will be. Similarly, if we have pointwise addition, then that will be element-wise addition. If we pick 10h, then that is applicable on single vector. Let's say I pick 1 and 2, then the 10h, pointwise 10h on this vector will be 10h of 1, 10h of 2. Okay, so these are nothing but pointwise operators that are applicable on vectors. Now the main thing here, that is, what is this rectangular box and why do we have sigma and tanh written over it? So these rectangles are nothing but single layer of neural network. It's a single layer, and how many nodes it will have? The number of nodes, the number of nodes will be equal to the number of elements in CT, HT, CT minus 1, whatever vector you may pick. Okay, so it's equal to the dimension of FT, we can say, because every vector is of equal dimension except XT. It can have a different dimension. Okay, so if there are three elements in FT vector or CT vector or HT minus 1 vector, then the number of nodes that will be there will be 3. Okay, so we decide how many nodes we want, and based on that, we have the dimensions of other vectors. Okay, and there is no particular logic that I know why these numbers are fixed, but this is the rule of LSTM. For simplicity, we keep the numbers same. Okay, we decide how many nodes we want, and then every other vector that is there will have the same dimension except xt. Okay, now we see here that there are these sigma and tanh that are written over these boxes. These are nothing but activation function in each of the node. Each of the node in the layer will have the same activation function. So if sigma is written, then every node in this layer will have sigma as activation function and tanh as activation function. Now why do we have different activation functions? Why do we have sigmoid? Why do we have tanh? And why are we not considering only one? So the reason is that your sigmoid activation function, for to understand that, you need to first understand that why do we use sigmoid and why do we use tanh. They both have different purposes. So we use sigmoid because this sigmoid tells how much value should it allow to pass. Okay, how much information should it allow to pass? Is it zero point 0.4 or is it 20% of the information that it has? How much information should it pass? But tanh, on the other hand, represents the actual information that flows. Actual information that flows. Okay, it can be positive, it can be negative, because tan h has a range of -1 to 1, while sigmoid has only range of 0 to 1. Okay, but why is it -1 to 1 and why not any other number? The reason is because we want normalized values, right? That is why we want everything on the same scale, and -1 to 1 is a comfortable scale for us. So that is why, to standardize everything, to normalize everything, we use tan h. And this tells you how much actual information that should flow. And when we will discuss the entire architecture in detail, you will appreciate that why we are using different activation functions and why not the same activation function everywhere. But remember this thing, that sigmoid is used to represent how much information should it allow to pass, and tanh is the actual information that flows. And once we will understand the architecture in detail, then this will become more clear to you. So I hope up till now all the notations are clear. Now inside this architecture, you can divide this entire architecture into three areas. This is the first area. This is the second area, and this is the third area. So let me highlight it. This is the first area. This is the second area, and this is the third area. And what do we call each of them? This is where LSTM forgets the unnecessary information. This is where the LSTM adds the necessary information. And this is the area where you get the output, or where the output is decided. Okay, so these are the three areas, and these are the gates. This is the first gate, this is the second gate, and this is the third gate. This is called the forget gate, this is called the input gate, and this is called the output gate. And we will discuss each of these regions separately, and then we will combine everything together so that everything comes out like a solved puzzle. So let's dive deep into each of those regions. And yes, I missed one thing, and that is YFT, IT, C-T, and OTR vectors, right? So and why their length is equal to 3. I mean, the number of nodes that we consider. That is because if you consider this box where we have these nodes with sigmoid activation function, then the output will come from each of these nodes, right? And this output together will form the vector. For example, the FT vector. Okay, let's say we got 0 0.4 here, we got 0 0.2 here, we got 0 0.1 here. So output from each node forms an element of the vector. And this is true for each of the other vectors that we have considered, since these are the outputs of these boxes. So every node is giving an output, and that is being stored as an element of that vector. So I hope now this part is clear. So now let's start with our first gate, and that is the input gate. I mean the forget gate, sorry. So if in one line I tell you that what exactly forget gate does, so it controls what information is removed from our memory cell. Okay, so this is our, let me create a rough architecture of what exactly is happening in the forget gate. So it's taking in HT minus 1, it's taking in HT minus 1, it's taking in XT, then we have a sigmoid neural network layer, and then we are giving FT as output. We have CT minus 1, and there is a pointwise operation, that is pointwise multiplication that is happening here. and we call this forget operation. So what this gate does, that it decides, it controls what kind of information, what information do we need to remove from our memory cell. And what is our memory cell? CT minus 1 is our memory cell. This is what our cell state is. This is what the long term memory that the LSTM is maintaining. So let's say from the previous LSTM we got a long term memory, but we want to, based on the current input and the previous hidden state, we want to decide that what information is no longer relevant and what information do we need to remove from this memory cell. We want to update it, right? We want to remove the unnecessary information that we think is not important based on the input that we have got and the previous hidden state. Okay, so what happens that xt, you have ht minus 1 and then you have some operate processing happening here, and then you're getting ft as output. So in forget region there are two things happening. First, we are calculating what ft is, and second, we are calculating that what what we are getting after this. So these are the two things that are happening in forget region. Okay, so let's understand one by one that what is ft, what ft represents, and what is ct minus 1 pointwise operation with ft. So what is happening here is that you have a neural network. Let's say we consider that the number of nodes are 3. So here we will have 3 nodes, and our ht minus 1 will also have 3 elements in the vector. Now xt can be of any length. Let's say we consider it as a vector of dimension 4, right? So these are the 4 elements. So this is our xt and this is our ht minus 1. These are going as inputs in this single layer of neural nodes, and then we are getting output which we are storing as ft. Okay, and this is nothing but fully connected artificial neural network, simple ANN, fully connected. Every input is connected to every node. Okay, it's fully connected artificial neural network. So how many weights will be there? There will be 21 weights here and 3 biases. Okay, and the output that is coming out from here, we are storing it in a vector which we call ft. So I hope the ft part is clear. Now I will tell you what the intuition behind ft is and what the intuition is behind this. But let's just first cover this part as well. That then we are we are doing pointwise multiplication between these two quantities. Okay, now this part is simple. Once we have the vectors, we just need to pick each element and each corresponding element of another vector, and we just need to multiply both of them. So I think the mathematical part is clear. Now the only thing that we have doubt with is what is the intuition, what exactly ft is doing, what exactly the pointwise operation is doing, and why do we call it forget gate, and why, how is it removing the information from the memory cell. So to understand this, you need to remember what I told you here, and that is about sigmoid activation function. What does it do? It decides how much information should pass, right? It decides how much information should pass. So you can, in a way, say that this vector is giving you the information that how much information should pass, and ct minus 1 covers all the information. It has all the information. It's our memory cell, right? So when we are multiplying ft with this, what is happening here? That it's selectively deciding what memory should pass on and what memory to drop. How much of the information that we have in CT minus 1 should be allowed to pass, right? And we know that sigmoid function can have value ranging from 0 to 1. So let's say ft is 0. That would mean that the final result that we will get from here, let's say we call it CT, then the final result that we will get from here will be a vector of zeros. Now, what does this represent? That every information was deleted. Nothing was allowed to pass on. And if this ft is 1, what would that mean? That every information was allowed to flow. Nothing was removed from CT minus 1, right? If let's say I pick ft equals to 0 0.5, that means half of the information was allowed to pass on and half of the information was removed. Our memory cell was forced to forget half of the information. That is why this gate is called forget gate. I hope the first part is clear. So now let's discuss the second gate, and that is the input gate. We will discuss about this region in detail now, and this is the architecture that I have created that exactly replicates this region. So what's happening here, that just like we calculated ft, we are same way calculating it. Okay, so basically in the input gate we do three things. First, we calculate ct dash, that is the candidate cell state. I will tell you all the intuition behind what this candidate state is. Second, we calculate it, and third, we calculate this ct. So these are the three things that happens within this input gate, and I think the it is clear. Just like in the forget gate, we calculated ft where we were taking in the ht minus 1 and xt as input, and then we had a single neural network layer where activation function was sigmoid, and then the output that we were getting was a vector which we called ft. Same here, we have it, same inputs, same neural network layer with every node having sigmoid activation function. There will be 21 weights and 3 biases, but of course their value will be different because from here we are getting a different output, right? But the basic intuition that we discussed there remains the same. This will tell you that how much information will it allow to pass. Okay, so it will tell that, it will decide what percentage of info will pass. Now let's move to the first part where we want to find C dash T. This C dash T is called candidate state, candidate cell state. This has a special name. And what this tells, what information does this tell? It tells that based on current input and the previous hidden state, what information does it think that we should add in the cell state. So it's like it thinks that this is the information that we must add in our memory cell. That is the long term memory that the LSTM carries. So this candidate cell state, it's like whenever in an election there are candidates who says, there are candidates who say that vote for us, but only one becomes the president or the prime minister or whatever post for whatever post the elections are being held. The same way, this candidate cell state contains all the information that it thinks is necessary we should put in inside our memory cell state based on the current input and the previous hidden state. So what activation function does it use? Tan H, because As I told you earlier, that tanh is used to represent the actual info that should pass. Sigmoid function only tells you how much information should pass. It decides that how much information, what percentage of information should pass. But tanh activation function actually tells you that what actual information, it's the actual information that passes, right? So tanh tells you that what information should pass. So that is why we are using tanh activation function in the neural nodes of this single layered neural network. And the output here is the candidate cell state that tells you that what information the network thinks that is it is important to put in the memory cell, or the long term memory that the LSTM is carrying. Now there is a pointwise operation that is happening here. What this pointwise operation is doing, that from the candidate cell state, it's deciding that how much information should pass, or basically what information from the candidate cell state is actually necessary, is actually required, is actually important for the final memory cell state. Okay, so it tells you that what information out of the candidate cell state is actually important, like who became the prime minister, who became the ministers at the end. Out of all the candidates, who became the ministers at the end. This is what this pointwise operation is doing. And once we have decided what will go as input, we take the memory cell state and we add it up there. Okay, so whatever we were getting from this part, now we decided that this information we need to add here. So that information is added, and the final output that we get, this is our memory cell state, and this is what becomes the input for the next LSTM. Okay, so I think this is, I'm sorry, so I think this is clear. You are calculating your candidate cell state, you are deciding that what information should pass, and then you are multiplying both of these to actually decide what information from the candidate cell state will be added to the memory cell state, and then you are calculating your final memory cell state. So I hope this is clear that why this region is called the input region and why this gate is called the input gate, because we decide here that what information we need to put in our memory cell state based on the inputs, that current input and the previous hidden state. So now let's move to our last gate, and that is the output gate. And what exactly we are doing in the output gate, we are calculating the output. We already have got our CT. The only thing that we are left with is the hidden state at current time step. Okay, and what we are doing here, that again we are deciding based on current input and previous hidden state, we are deciding that how much information should flow. Okay, and what we are doing here, that we are applying first tan h operation on cell state. We will see that why we are applying tan h pointwise operation on cell state, because you see here that cell state can be a vector of real numbers. It can have real valued elements, right? But what we want is normalization or standardization, where every value is within a certain range of -1 and 1. And we want to maintain the negative and positive signs, because that represents that what information is being removed or what information is being added, right? It gives a more figurative value. For example, increase value of a specific feature in memory, right? Or decrease or undo the feature in memory. For example, let's say I have a CT vector like -4, 10. This represents the negative sentiment and this represents the positive sentiment. So this clearly tells that negative sentiment is very low. That means there are very high chances that the movie review that we have is has a sentiment of positive, has a positive sentiment, right? So we convert them, we squash them within a certain range of -1 and +1. That is the range of tan h. And second, what we are doing, that we are taking the output vector. So the vector that is coming out from here is called OT. We are taking this vector and we are doing pointwise multiplication of it with our new CT. So this will become our, we will not call it CT because that is what coming out from here as output. But this is a more squashed version of CT where we are just squashing it down within a certain range of -1 and +1 and maintaining everything that it has, right? So I think this part is clear mathematically and intuitively both. Let's just come to this part, that what exactly are we doing here. So as I told you that OT is nothing but, if we just go up, it takes in the input xt based on the input based on the previous hidden state. It, this information flows to a neural network that has a single layer where every activation function is sigmoid, and the output that we are getting from here is called the OT vector. So as you know that the intuition behind using sigmoid is that it decides how much information, what percentage of information will flow, right? So when we are multiplying it with tan h, it's deciding that what information from CT should actually become a part of current hidden state. So your long-term memory contains everything. It contains the selective memory that you wanted to remember, that the LSTM wanted to remember. Now, out of this full memory, out of this selective full memory, you want to decide that how much information should actually pass or what exactly will become the current hidden state which will be necessary for the next LSTM, right? Or the next or the final output. So this is what our output gate is. I hope this entire architecture is clear. You first of all you decide that from your memory cell what information you want to forget based on your input and previous hidden state. Then you decide what information do you want to add based on your inputs, what information is necessary that our long term memory should capture, and then we decide that what will be our hidden state, what will be the final output. So the final output will be that out of that long memory, long selective full memory that we have, this is the information, this is the output that we have got. So HT is like the final output, or if we have another LSTM, then that will act as a previous hidden state. Okay, it is short term memory, like what exactly we have got as output currently. So I hope the entire functioning of this LSTM is clear, and I hope that this complicated architecture I have made simpler for you. And now everything is clear. If you still feel that some part or some specific notation or some specific part of the video was not clear, do tell me know in the comment section, and I will clear all your doubts. I promise. And let me know in the comment section that whether you like this video or not. I try to cover not only the mathematical aspects of it, but also the intuition behind why do we have separate layers, why do we have separate notations, why do we use specific activation functions. And I know as compared to RNN, this architecture is quite complex, but I think now everything to you is clear. So if this video took a lot of hard work, so if you really liked my video, please give it a thumbs up and subscribe to my channel. Thank you.